Module 6, Lesson 15, more practice with box plots. So in the last couple of lessons we have taken a look at the 5-number summary and we have looked at box plots, and now we're going to explore a little bit more with box plots. I can read a box plot and give estimates of the values that make the 5-number summary. So we will look at the box plot and come up with the 5-number summary. I can describe a data set using the 5-number summary and interquartile range. I can construct a box plot from a 5-number summary. So you reach into a jar of Tootsie Pops, and how many Tootsie Pops do you think you could hold in one hand? Do you think the number you could hold is greater than or less what other students can hold? Is the number you could hold a typical number of Tootsie Pops? So pause for a moment, think about those 4 questions. Think about what would affect your answer to these questions. So the 5-number summary. A 5-number summary are the numbers needed to construct a box plot. We have the minimum, the lower quartile or Q1, the median, the upper quartile or Q3, and the maximum. So looking at this example, 94 people were asked to grab as many Tootsie Pops as they could hold. Here is a box plot for these data. Is there anything here that surprises you as you look at this, thinking about your answer to how many Tootsie Pops do you think you could hold, the range? Was there anything looking at this that surprises you? Maybe you're looking and thinking, wow, somebody was able to grab like over 40. You're thinking, man, somebody had really small hands. They could only grab like 5 or 6. Were you surprised to see kind of what the middle section is? Were you interested to put your own number on there? I think I thought of Tootsie Rolls instead of Tootsie Pops, although maybe they're the same thing. So I was thinking whole bunch, but maybe if they're talking about Tootsie Pops, which are the suckers, then maybe I'm thinking I can hold less. I don't know. So what might explain the variability in the number of Tootsie Pops that the 94 people were able to hold? Well, how big are people's hands? What is their hand span? Meaning when they hold up their hand, how wide is their hand? Does it matter how flexible their fingers are? Does it matter how strong their fingers are? Does it matter how big the jar is? Using the box plot, estimate the values in the 5-number summary. So we're going to look at this box plot and we're going to try and figure out about what these numbers are. So we take a look here at the minimum, and I can see the minimum is somewhere between 5 and 10, so I'm going to estimate that as probably being about 7. And the maximum is between 40 and 45, almost halfway, so I could probably do 42 or 43. I'll put 42. The median, the middle number, boy, that looks really close to 20. Quartile 1, which is the left side of the box, well, that's less than 20, but it looks closer to 20 than 15, so I'll estimate that as 18. And looking at quartile 3, which is this side, that looks about halfway between 20 and 25, so I could even estimate that as being 22.5. Now remember, these are estimates. So even now I'm going to push the button here, and you're going to see that my estimates don't got a typo there definitely, but my estimates don't perfectly line up with what I typed into the Google Slides, and obviously I need to fix that maximum there. So describe how the box plot could help you understand differences in the numbers of Tootsie Pops people could hold. So looking at this box plot right here, what can I see there that could help me understand the differences that are occurring here? Well, the maximum of about 42 and the minimum of about 70 indicate that there is a lot of variability. we are spread out a very long ways on how many Tootsie Pops people were able to hold. It covers a range of about 35. The box part, this center section, shows that about half of the people can hold within about 2 Tootsie Pops of the median. So I've got the median here of about 20, and this is about 18, and this is about 22. I've got half the people in this space, and they're 2 this way and 2 this way. Let's see, there were 94 people. That means I've got, what, 47 people are in this little teeny tiny space here, and then this piece over here is half of 47, and this piece over here is half of 47. So looking at the box plot, half of the people are in this itty bitty space, and then I have all this spread out room on the sides. So just looking at the box plot, I can already see that the differences in the numbers of Tootsie Pops, I can say, yes, there is a huge range, but I can say half the people fit into this little small area in the middle. So here's Jane's description of what she sees in the box plot. And do you agree or disagree with her description, and explain your reasoning? She says one person could hold as many as 42. The number of Tootsie Pops people could hold was really different and spread out about equally from 7 to 42. Is it spread out? Let's see, about 1/2 of the people could hold more than 20 Tootsie Pops. So is Jane's statement correct? Well, it is correct. We could go from 42 to 7. Okay, so we could have as many as 42. Yes, that's a true statement. The number of Tootsie Pop people could hold was really different and spread about equally from 7 to 42. Now that's a big question. Is it spread equally from 7 to 42? And then Jane says about half the people can hold more than 20 Tootsie Pops. Sorry, about half the people. So here's the middle to here. Well, that's a true statement. I've got a quarter here, and a quarter here. So about half the people could hold more than 20. That's a true statement too. But is this data spread equally from 7 to 42? This statement, her first statement, yes, it's true. This is a true statement. This is a true statement. But I don't feel very good about 7 to 42. I cannot tell that they are evenly spread. Sorry, you cannot tell that they are evenly spread. The box has half of the people, and I already made a big deal about this, half of the people are in here, and then we've got all of this spread out on the sides. Looking at this box plot, we can tell that it is not spread evenly from 5 to 42. So Jane's description is not a very good description, even though she did have 2 true statements. So here's a different box plot of the same data on the number of Tootsie Pops 94 people could hold. So this is a box plot, but it's a little bit different kind of box plot. So what do you suppose these 5 values that are kind of by themselves and have these little stars under them, what do you think's going on with those? Well, these are values that are far away from most of the other values. So what they've done is taken what are called the outliers, the numbers that really don't fit with the rest of the data, and they have separated that. And what they are left with are the other 89 values on this box plot. So most of the data actually goes from 12 to 27. Now, as we look at this, do we think that the data is spread a little bit more evenly? Things to think about. So does knowing these data values, so in other words, knowing this and these, are kind of out there and that the other 89 are right here, does that change anything about your answers to questions 1 through 4? Well, not really, except to maybe say that only a few people could hold more than 30 Tootsie Pops, and that the rest held fewer than that, and only a few people could hold 10 or fewer Tootsie Pops. So it doesn't change too much about exercises 1 through 4. And Jane's answer about whether or not this is spread equally, not really. It's still not very equal. We've got a really tight section in the middle, and we're still more spread out. So we can't say the data is spread equally. All right, so here are a couple of tables, and these are the maximum speeds of selected birds and land animals. So as we look at this table, we've got the names of birds and how fast they go in miles per hour, and we have animals and their speed in miles per hour. So pause for a moment, take a look at the table. What observations can you make? Maybe do some comparison table to table. What are some things that stand out to you? Some things you go, oh, that's interesting. In particular, be looking at the data and comparing what you see happening. So one of the fastest recorded speeds for a human was 27.79 miles per hour for Usain Bolt during a 100-meter sprint in 2009. How does this human speed compare to the other land animals? Where does Usain Bolt's speed fit? Well, 27.79, that gets him in kind of at the bottom of the recorded land animals. It kind of is the same, a little bit faster than an elephant and maybe a little bit smaller than wildcats. And Usain Bolt was considered to be one of the fastest humans ever. So that gives you an idea there. So as we look at the speeds, what stands out to you as being interesting? I asked you to take a moment, do a little looking, make some comparisons. What was interesting to you? I noticed that the birds are really fast, especially the falcon at 242 miles an hour. The ostrich goes 60 miles an hour. That's pretty fast. Only 2 of the speeds had decimals. I thought that was kind of interesting. The rest of them were rounded to be whole numbers. I thought this last comparison was very interesting. The fastest of the land animals, the cheetah, the bat, they fit in right down here at the bottom of the birds. So the slowest birds are almost as fast as the fastest land animals. Wow, those birds, they move pretty fast. So do birds or land animals seem to have the greatest variability in speed? So now we're looking at a layer deeper. We're asking what we see in the way of variability as we look at the actual data. Where do we seem to see the greatest variability? Well, it looks like the speeds of the birds, they vary a lot as they go from 60 miles an hour. So we have a range going from 60 to 242, which is a range of 182 miles per hour. Where with the land animals, we've got 75 going down to 9, and we've got a range then of about 66 miles per hour. That's almost 1/3 of the 182 miles an hour. So looking, we really have a lot of range for the birds, and not as much range for the land animals. Now it is interesting to perhaps remove the peregrine falcon from this conversation And now we've got 120, and we take away 60, and we've got a range of about 60. And let's just, for comparison, take off the cheetah here, and we've got 60 down to 9, and we've got a range of 51. So if we take away the two top speeds, all of a sudden the ranges look a whole lot closer. So we need to be careful as we look at data, looking and saying, do we have some data there that is changing things in a big way? But we do appear to have, just looking at what's here, greater variability with the birds, a little bit less variability with the land animals. So here we're going to find the 5-number summary for the speeds in each data set. And we're going to ask ourselves, what do the 5-number summaries tell you about the distribution of speeds for each data set? So you'd want to pause here, and you'd want to get out your piece of paper. This is in your math workbook. You'd want to go through here, and you'd want to find your 5-number summaries. So pause the video, take a few minutes and do that. Here's the 5-number summary for the birds. The minimum is 60. Quartile 1 is at 76. The median is at 97.5. Quartile 3 is at 105.5. And a maximum of 242. For the land animals, we have a minimum of 9, a maximum of 75. Quartile 1 is at 32.5. Quartile 3 is at 50. And the median is at 43 and 97/100ths. Now, what do the 5-number summaries tell us about the distribution of speeds for each set of data? The summaries give me a sense, an idea of the range or span of the speeds, so comparing maximum minus the minimum, and how the speeds are grouped around the median. So I can look here, quartile 1 and median and quartile 3, quartile 1, median, and quartile 3. I get a sense of how we're spread around the median. I'm going down about 11, and I'm going up about 8. I've got a total of about 20 there. Here I'm going down about 21, and I'm going up only about 8. I've got a total of about 30. So I can look inside of the 5-number summary and see what's happening with the middle part of the data. So I have the total range of the data, which is the maximum compared to the minimum, but then I also have the comparison of the middle part of the data using the 3 middle numbers of the summary. So we're going to pause here, use the 5-number summaries to make a box plot for each of the 2 data sets. And I will do the birds, and then you need to pause and do the land animals, and then you can compare yours to mine. So the birds are a minimum of about 60, so I'm going to put a dot there at 60. Quartile 1 is at about 76, so I'll go ahead and put a line there. And I've got a median of 97.5, so I'm going to say that's right about here. Quartile 3 is at 105.5, so that's going to be right about here, and I'm going to connect my box there. And I've got a maximum of 242, which is right about there. And I need to do a little connecting here, and I've got my box and whiskers, which we call a box plot or a box and whiskers. So go ahead, pause, and go ahead and take care of the land animals. All right, so hopefully you have finished your land animals, and you can compare your box plot to the box plots that I have here on the screen. And this is a great time to pause for a moment and just look and ask yourself, so what do these box plots help me see as I compare the speed of birds with the speed of land animals? So take a moment and write several sentences describing the speeds of birds and the speeds of land animals. So pause here and think, how can you summarize in words what you are seeing here? So I can make some statements. At least one bird flies really fast, the falcon at 242 miles an hour. 3/4 of the birds fly less than 106 miles an hour. I've got 3/4 here because you'll remember that this is a fourth, this is a fourth, and this is a fourth. So 3/4 of the birds are less than 106 miles an hour. I can say that the slowest bird flies 60 miles an hour. I can look at the land animals and say the land animals' running speeds are slower. They range from 9 to 75. I can say that the middle half of the speeds is between 32.5 and 50 miles per hour. So notice that these aren't really fancy sentences, but we are just making simple, true statements about the data. So for exercises 11 through 15, we're going to do a little bit of comparison. We have 3 box plots here. We're going to look for what is the same, and we're going to look for what is different. Each of these box plots show the number of correctly answered questions on a 20-question quiz for students that are in 3 different classes. So we have Class 1, Class 2, Class 3. They all took a 20-question quiz. All of their box plots are based off of the same quiz. Same quiz, 3 separate classes. So describe the variability in the scores of each of the classes. What do we see with each of the classes in terms of variability? Now, before we go any farther, I want to point out something about Class 2. Some of you are probably thinking that we're missing some information here. Well, sometimes when we make a box plot, our minimum and maximum values end up being right on quartile 1 and quartile 3. So we don't have any of those lines sticking out, any of those whiskers. So even though you can't see them, we do have a minimum value and a maximum value. They just happen to also be right on top of quartile 1 and quartile 3. Now you should pause for a moment and you should ask yourself, how would that be possible? And the answer is, what if we had a whole bunch of people who scored 5 and a whole bunch of people who scored 20? Would it be possible then for the minimum to also be quartile 1 and for the maximum to also be quartile 3? All right, here we go. Looking at some variability. So the range, the maximum minus the minimum, is the same for all 3 classes. The maximum for each and every one of them is 20, and the minimum for each and every one of them appears to be 5. So they're all covering a range of about 15. That's interesting. They all have the same range, but we're seeing 3 very different box plots. The big difference that we see is in the middle section. Looking at the middle 50%, the middle half, as it were. Class 2 is very spread out across the middle section. Class 3 has a very small distribution across the middle, and of course Class 1 is kind of in between. Class 3 has a small box, so the scores in the middle are close together. In Class 2, the minimum and lower quartile are the same score. We already talked about this. And the maximum and the upper quartile are also the same score. So lots of scores are piled at the ends of each range. Lots of their scores are going to be out here. Where on Class 3, they're very close together in the middle. The middle half of scores in Class 1 are spread out more than Class 3. So they're more spread out than Class 3, but not as much as Class 2. Interesting. And of course, as a teacher, I'd be curious to know what happened. So taking a look at these, let's estimate the interquartile range for each of the 3 sets of scores. So if we say that this one's at about 18.25, and this one's at about 7.75, what would the interquartile range be? So 18 1/4 minus 17 3/4. What are we left with here? Looks like they have a range of about half, 7 3/4. They have a range of about 10 1/2. Looking at class 2, we've got 5 and 15. They've got an interquartile range of 15. And looking at class 3 here, boy, that looks like, 14 1/2. And we've got about probably 9 1/2. So the interquartile range, and remember, these are just estimates. Just estimates. I've got an estimate of about 10 1/2, an estimate of 15, and an estimate of 5. And the teacher materials estimated them at 10, 15, and 6. So I'm in the ballpark. Same range, minimum to maximum, but the interquartile ranges are very different. So what fraction of students would have scores in the interval that extends from the lower quartile to the upper quartile? Normally we would say about 50% that extend from the lower quartile to the upper quartile. We'd say about 1/2. Class 2 is kind of interesting because we know it's all of the students, but we would still say it would normally be about half. So what does the value of the interquartile range tell you about how the scores are distributed? Remember, we had about 10 1/2, we had 15, and we had 5. Well, we can look and say that class 2 is very spread out, class 3 is not very spread out at all, and class 1 is about halfway in between the two of them. So for class 1, half the scores are spread over an interval of a width of 10. So half the class fits in this area of 10. For class 3, they're in an area of 5, and for class 2, an area of 15. And included in that, we actually have more than half. We have all of their data fits in that range of 15. So which class do you believe performed the best? Be sure to use information from the box plots to support your answer. So as you look at this data, as a teacher, you're asking yourself, which of these classes did the best? Which would you pick and why? And it's more important that you can explain your reasoning than it is that you get the right answer. So class 3 has the smallest interquartile range. About half the students were close to the median. So their scores were more consistent. So if your goal as a teacher that you have consistent scores, class 3. As we look at class 1, about 25% of the students in class 1 scored 18 or higher. So I've got 1/4 of my class that is scoring very high. So and that's compared to 25% on class 3 that scored about 15 or better. So if we want to look at how many kids scored high, class 1, we could say class 1 did better. In class 2, we must have had several students who scored near the top in order for quartile 3 and the maximum to be the same. So I could look and say, well, I had even more kids in class 2 that scored high. So depending upon how you want to measure it, you can answer the question, which class scored the best? Now, me personally, I like to see consistency. I would probably say that class 3 would be the class who did the best. They are nice and consistent in their scores. As a teacher, I can help this group of students improve. I can help the kids in the other two classes, but it's going to be much trickier. Class 2, we probably had kids who scored really high and kids who scored really low, so I have a class that's kind of half and half. Class 1 looks a little bit more evenly distributed. I've got a little bit of my class in every one of the spots. Class 3, I can look and say, okay, here is what I taught well, here is what we need to work on. So I personally prefer consistency, but that's just me. So exercise number 14, I'm going to skip that. Finding the interquartile range for the 3 data sets that we looked at, the land animals, the birds, and the Tootsie Pops. So if you want to look at that one, the answer is here, but I'm going to skip that question. And exercise 15. A teacher asked students to draw a box plot with a minimum value at 34 and a maximum value at 64 that had an interquartile range of 10. Jeremy said he could not draw just one because he did not know where to put the box on the number line. Do you agree with Jeremy? Why or why not? Remember, Jeremy says he could not draw just one. So Jeremy's saying there's more than one way for me to do this. Do you agree with Jeremy? Why or why not? Jeremy's correct. A box with a width of 10 could be drawn anywhere between the minimum and maximum values. So that middle box could be moving around as long as the interquartile range is 10. Nice job, Jeremy. All right, so quick closing here. So what are the values included in the 5-number summary? So stop and think about that. What goes into the 5-number summary? We've got the minimum, the lower quartile, the median, the upper quartile, and the maximum. These are the 5 numbers in the 5-number summary. What does it mean when the box part of the box plot is very small? So when I have a box plot and I've got my box very small, what does that mean? It means that the middle half of the data values are bunched up near the median and that the interquartile range is a small number. It means we don't have very much variability. All right, so concluding the lesson, I can read a box plot and give estimates of the values that make the 5-number summary. I can describe a data set using the 5-number summary and interquartile range. And I can construct a box plot from a 5-number summary. So that concludes Module 6, Lesson 15. If you've got questions, make sure you ask them, and make sure you complete your problem sets and your exercises.